study motion changing position. At the same time, we try to discover physical quantities which do not change in the physical process, which do not change in a physical process. The laws of momentum and energy conservation are typical examples. In this section, we shall apply these laws to commonly encountered phenomena, namely collisions. Several games such as billiards, marbles, or carom involve collisions. We shall study the collisions of two masses in an idealized form. Consider two masses m1 and m2. The particle m1 is moving with speed v1. The subscript I imply initial. We can consider depicted in figure 5.10. M1 coming here, Martin collides with mass m2, which is at rest. They both split with the directions which cause theta 1, theta 2. Collisions of mass m1 with the stationary mass m2. The masses m1 and m2 fly off in different directions because of collision. We shall see that there are relationships which connect the masses, the velocities, and the angles. Elastic and inelastic collisions. In all collisions, the total linear momentum is conserved. Total linear momentum is conserved in all collisions, whatever the collisions might be. The initial momentum of the system is equal to the final momentum of the system. One can argue this as follows. When two objects collide, the mutual impulsive forces acting over the collision, time delta t causes change in their respective momentum. That is, delta p1 equals to f1 1 is to 2 of delta t, delta pt equals to f2 is to 1 of delta t, where f12 is force exerted on first particle by the second particle and force 21 is likewise the force exerted on the second particle by the first particle. Now from Newton's third law, f1 by 2 equals to minus of f2 by 1. This implies that delta p1 plus delta p2 equals to 0. So here it's proved that linear momentum is conserved in all cases. The above conclusion is true even though the forces vary in complex fashion during the collision time delta t. Since the third law is true at every instant, the total impulse on the first object is equal and opposite to that on the second object. On the other hand, the total kinetic energy of the system is not necessarily conserved. Not necessarily conserved. The impact and deformation during collision may generate heat and sound. Temperature changes, sound generates, heat is generated or lost. Part of initial kinetic energy is transformed into other forms of energy. Part of initial kinetic energy is transformed into other forms of energy. A useful way to visualize the deformation during collision is in terms of compressed spring. If the spring connecting two masses regains its original shape without loss in energy, then the initial kinetic energy is equal to the final kinetic energy, but the kinetic energy during the collision delta T is not a constant. Such a collision is called an elastic collision. On the other hand, special concept, but the kinetic energy during the collision of delta T is not a constant. Such a collision is called elastic collision. On the other hand, the deformation may not be relieved, and the two bodies could move together after the collision. A collision in which the two particles move together after collision is called a completely inelastic collision. The intermediate case where the deformation is partly relieved and some of the initial kinetic energy is lost is more common and is appropriately called an inelastic collision. Collisions in one dimension. Consider first a completely inelastic collision in one dimension. Then theta 1 equals to theta 2 equals to 0, m1 initial equals to m1 plus m2 to the v final, momentum conservation, and v final equals to m1 by m1 plus m2 into v1 of initial. The loss of kinetic energy of collision is delta half mv squared minus half m1 v1 to the v final. Then this is the whole process, which is a positive quantity as expected. Consider an elastic collision using the above nomenclature with theta equals to 1, theta equals to 2 equal to 0. The momentum and kinetic energy equations are m1 v1 equals to m1 v1 plus m2 v2, m1 v square equals to m1 v square plus m2 v2 square. From equations 5.23 and 5.24 follows that m1 v1 to the whole of v2 minus final minus initial equals to m1 v1 of v2 final minus v1 initial, or this process. Hence, therefore, we can conclude that v2 final equals to v1 initial plus of v1 final. Substituting this in equation 5.23, we obtain that v1 final equals to m1 minus m2 by m1 plus m2 into v1 initial, and v2 final equals to 2m1 v1 by m1 plus m2. Thus, the unknowns, that is v1 and v2, are obtained in terms of knowns m1, m2, v1. Special cases of our analysis are interesting. Case 1. If two masses are equal, v1 equals to 0, v2 equals to v1. The first mass comes to rest and pushes off the second mass with its initial speed on collision. So basically the first mass comes to rest when two masses are equal. First mass comes to rest because of the initial velocity. When it pushes the second mass, comes at the rest position, and its energy is exerted to the second mass, due to which it starts an initial speed of velocity. It starts to be in motion. Yes, if one mass dominates, that is m2 is very much greater than m1, then v1 is approximately equal to minus of v1, and v2 final is equal to approximately 0. The heavier mass is undistributed while the lighter mass reverses its velocity. Heavier mass is undistributed, lighter mass reverses its velocity. Slowing down of neutrons is an important example. In a nuclear reactor, neutron of high speed typical 10 to the power 7 must be slowed to 10 to the power meter per c, so it can have high speed probability of reacting the isotope uranium and causing it to give the fusion, nuclear fusion, so that a neutron can lose most of the kinetic energy in a sequence and light nuclei like deuterium or carbon, which has mass of only few times the neutron mass. The material making up the light nuclei, usually heavy water D2O or graphite, is called a moderator. So what should we solve? We should show the mass in both of the collisions, that is slowing down of neutrons. Okay. The initial kinetic energy of neutron is K, kinetic energy half mv square always. But let's find final kinetic energy from equation 5.26. We can get that half m1 minus m2 by m1 plus m2 to the whole square. That is like k1 by k. This is nothing but k1 by k. So the fraction, yeah, the same thing. The fraction kinetic energy lost is k1 by k, like that, m1 minus m2 by m1 plus m2 to the whole square. Well, the fraction kinetic energy gained, fractional kinetic energy gained, this is lost by the moderating nuclei, that will be k2 by k1. k2 by k1, that's nothing but 4m1 m2 by m1 plus m2 to the whole square. 4m1 m2 by m1 plus m2 to the whole square will be k2 by k1. One can also verify this result by substituting from equation 5.27, the second one. Yeah, that works. For deuterium, m2 equals to 2m1, and we obtain f1, if that is final, equals to 1 by 9, while f2 equals to 8 by 9. Almost 90% of the neutron's energy is transferred to deuterium. 90% is transferred to deuterium. For carbon, f1 71.6% and f2 28.4%. In practice, however, this number is smaller since head-on collisions are rare. So basically, head-on collisions in practical physics, it's rare. So if initial velocities and final velocities of both bodies along the same straight line are along the same straight line, then it is called a one-dimensional collision or head-on collisions. We don't always notice head-on collision or one-dimensional collision. It's quite rare in real life. So in the case of small spherical bodies, this is possible if the direction of travel of body 1 passes through the center of body 2, where the center of mass is, okay, which is at rest. In general, the collision is two-dimensional, where the initial velocities and final velocities lie in a plane. Whenever we see any collision which is acting upon a plane, like x, y, any plane, then it automatically comes under two-dimensional. Basically, they won't be in the same direction, so it's like two-dimensional. Collisions in two dimensions. Now, 5.10% depicts the collision of a moving mass m1, that is the example. The stationary mass m2. Linear momentum is conserved. Linear momentum is conserved, like nothing to talk about that in such a collision. Since momentum is a vector, this implies three equations for three directions. As always, in the plane x, y, z axis. Consider a plane determined by the final velocity directions of m1 and m2, and choose it to be the xy plane. The conservation of the z component of the linear momentum implies that the entire collision is in the xy plane. The x and y component equations are here, where the trigger comes to the plane, where we can take the cos theta sin theta based on the angles. M into v equals to mv cos theta plus mv cos theta 2, And again mv equals to 0 because it's of the origin. Then m1 b1 sine theta minus m2 v2 sine theta, like the sine theta level of cos theta, the parabolic equation projectile motion. One knows m1 m2 and b1 in most situations. There are thus four unknowns here, like we don't know anything here, and only two equations. If theta 1 theta 2 equals to 0, we regain equation 5.23 again from one dimensional collision. That is, if further the collision is elastic, then again we get half m1 v1 equals to half m2 v2 square plus half m2 v2 square final, like initial and final, we add here. We obtain an additional equation that still leaves us one equation short. At least one of the four unknowns, say theta 1, must be made known for the problem to be solvable. For example, theta 1 can be determined by moving a detector in an angular fashion from the x to the y-axis, given m1, m2, v initial equals and theta 1. We can determine v1 final, v2 final, theta 2 from equations 5.28 and 5.30. 28, okay, this and 5.30 we can determine, but if something is given without substituting any theta over here, we can't determine. It will come in the formula. Consider the equation depicted in figure 5.110 to be between two billiard balls with equal masses m1 and 2. Masses are equal, so it's constant. The first ball is called the cue while the second ball is called the target. The billiard player wants to sink the target ball on a pocket which is at the angle theta equals to 37. 37 take permission. 37 assume that the collision is elastic collision, and that friction and rotational motion are not important, so ignore them. We have to obtain the theta. We know theta 1, we know theta 2, that is of the billiard basically. We don't know the theta 1, meaning the hitting of the ball. For momentum conservation, since the masses are equal, we can take linear law of conservation of linear momentum, that is v equals to before collision and after collision, and substituting the formula is like this. The same thing, v1 final plus v1 square of final plus v2 square of final plus, it's the identity a square plus b square, a plus b to the whole square, identity including cos theta. Basically the vector identity, as we know theta 1, we can just take theta 1 as theta 1 and theta 2 as we're already given, we can take it as 37 degree. And since the collision is elastic, m1 m2 equals to m1, it follows from conservation of kinetic energy that v1 initial square equals to v1 final square plus v2 final square. Comparing equation 5.31 and comparing equation 5.32, we get cos theta 1 plus 37 degree equals to 0. So theta 1 equals to 37 degree which equals to 90 degree. Meaning cos we are taking here as 90 degree. So substituting this side, theta 1 equals to 90 minus 37, which is nothing but 53. So that's how we get the theta. Basically m will get cancelled out there as we have 2 over here. 2 comes this side. And 90 cos theta 37 quadrant 2, so it lies in quadrant 2, we can take 90 as it is anything above 90 but by 180, so we take 90 as the basic ratio. Right. This proves the following result. When two equal masses undergo a glancing elastic collision, with one of them at rest after the collision, they will move at right angles to each other, where in two dimensions only they move at right angles to each other. So we take 90 again. The matter simplifies greatly if we consider spherical masses with smooth surfaces and assume that collision takes place only when the bodies touch each other. This is what happens in the games of marbles, carom, billiards. In our everyday world, collision takes place only when two bodies touch each other. But consider a comet coming from far distance to the sun, or alpha particle coming towards the nucleus and going away in some direction. Here we have to deal with forces involving action at a distance. So here they don't collide, but still we have to involve with action at a distance. Such an event is called scattering, like scattering of light. The velocities and directions in which the two particles go away depend on their initial velocities as well as the type of interaction between them. Because of their interaction, we can determine whether they're going away. Their masses, shapes, and size. All of these play an influence of why they're going away, why they're coming nearby, everything. So this is the summary of the whole chapter. Points to ponder. The phrase calculate the work done is incomplete. We should refer or imply clearly by context to the work done by a specific force or a group of forces on a given body over a certain displacement. Work done is a scalar quantity. It can be positive or negative, unlike mass and kinetic energy, which are positive scalar quantities. Kinetic energy can never be negative, it's always positive. So the work done by the friction or viscous force on a moving body is negative. Work done by the friction or viscous force on a moving body is negative, like it's an opposite direction. For two bodies, the sum of the mutual forces exerted between them is zero. From Newton's third law, we can derive every action has its own and equal opposite reaction in the same thing. But the sum of the work done by the two forces need not always cancel out each other. Like the sum of work may not cancel, but the forces do cancel out. So, however, it sometimes may be true based on the work they do. Like if they are so similar, then they do cancel. The work done by a force can be calculated sometimes, even if the exact nature of the force is not known. By not knowing the exact force, also we can calculate the work done. This is clear from example 5.2, where the work energy theorem is used in such a situation. So, on the basis of work energy theorem, we can derive work done on any given substance or any data. The work energy theorem is not independent of Newton's second law. It's not independent, it's dependent on Newton's second law. The work energy theorem may be viewed as a scalar form of the second law. It's told always like the work energy theorem is the scalar form of Newton's second law. The principle of conservation of mechanical energy may be viewed as a consequence of the work energy theorem for conservative forces. Well, the work energy theorem holds in all inertial frames, It can also be extended to non-inertial frames provided we include the pseudo forces in the calculation of the net force acting on the body under consideration. The potential energy of a body subjected to a conservative force is always undetermined up to a constant. It's not determined exactly for a constant. So, for example, the point where the potential energy is zero is a matter of choice. Like it can be either at the origin or at the final. It can be zero anywhere, it's upon the person who solves it. For the gravitational potential energy mgh, the zero of the potential energy is chosen by the ground. So for the spring potential energy kx square by 2, the zero of the potential energy is the equilibrium position of the oscillating mass. So it depends. Every force encountered in mechanics does not have an associated potential energy. Every force does not have associated potential energy. For example, work done by friction over a closed path is not zero, and no potential energy can be associated with friction. It's a non-conservative force, by the way. During a collision A, the total linear momentum is conserved at each instant of the collision. Total linear momentum is conserved at each instant of collision. During the linear momentum is just conserved. So the kinetic energy conservation, even if the collision is elastic, applies after the collision is over and does not hold at every instant of the collision. So kinetic energy you can only calculate or observe after the collision. It's not necessary that kinetic energy before and after will remain same as the momentum is. In fact, the two colliding objects are deformed and may be momentarily at rest with respect to each other. They get formed, deformed. So if it's at rest, then kinetic energy is zero. So it depends. System of particles and rotational motion. So up to in the earlier chapters, we have primarily considered the motion of a single particle. A particle is ideally represented as a point of mass and no size. We applied the results of our study even to the motion of bodies of finite size, assuming that motion of such bodies can be described in terms of motion of particles. Any real body which we encounter in daily life has a finite size. In dealing with the common motion of extended bodies of finite size, often the idealized model of particle is inadequate. Model is inadequate. In this chapter, we shall try to go beyond this inadequacy, meaning we go beyond inadequacy. Let's see quickly. We shall attempt to build an understanding of the motion of extended bodies. An extended body, in the first place, is a system of particles. We shall begin with a consideration of motion of the system as a whole. The center of mass of the system of particles will be a key concept here. We shall discuss the motion of the center of mass. Center of mass is a key concept of system of particles and usefulness of this concept in an understanding the motion of extended body. A large class of problems with extended bodies can be solved by considering them to be rigid bodies. Ideally, a rigid body is a body with a perfectly definite and unchanging shape. Perfectly definite and unchanging shape is a rigid body. The distances between all pairs of particles of such a body do not change. It is evident from this definition of a rigid body that no real body is truly rigid. No real body is truly rigid. since real bodies deform under influence of forces. But in many situations, the deformations are negligible. In a number of situations involving bodies such as wheels, tops, steel, beams, molecules, and planets, on the other hand, we can ignore that they wrap, twist out of shape, bend or vibrate, or treat them as a rigid. What kind of motion can be a rigid body have? Let us try to explore this question by taking some examples of the motion of rigid bodies. Let us begin with a rectangular block sliding down an inclined plane without any sidewise movement. The block is taken as a rigid body. Its motion down the plane is such that all the particles of the body are moving together. That is, they have the same velocity at any instant of the time. The rigid body here is in pure translation motion, like going in the same direction. The system of particle does not change. In pure translation motion, in at any instant of time, all particles of the body have the same velocity, like I said. Consider now the rolling motion. Rolling motion of a solid metallic or wooden cylinder down the same inclined plane. The rigid body in this problem, namely the cylinder, shifts from top to bottom of the inclined plane and thus seems to have translational motion. But as figure 6.2 shows, all these particles are not moving with the same velocity at any instant. The body therefore is not in pure translational motion. This motion is translation plus something else with it. So in order to understand what this something else is, let us take a rigid body constraint that it cannot have translational motion. So the most common way to constrain a rigid body so that it does not have translation motion is to fix it along a straight line. The only possible motion of such a rigid body is a rotation. The line or fixed axis about which the body is rotating is its axis of rotation. If you look around, you will come across many examples of rotation about an axis. A ceiling fan, a potter's wheel, a giant wheel in a fair, a merry-go-round, and so on. All come under rotational motion. So let us try to understand what a rotation is, what characteristics rotation. You may notice that in the rotation of a rigid body about a fixed axis, every particle of the body moves in a circle very well, which lies in a plane perpendicular to the axis, 90 degrees to the axis, which has its center on the axis. And 6.4 shows the rotational motion of a rigid body about a fixed axis, the z-axis of the frame reference. Let P1 be a particle of the rigid body, arbitrarily chosen and at a distance r1 from a fixed axis. The particle P1 describes a circle of radius r1 with its center C1 on the fixed axis. The circle lies in a plane perpendicular to the axis, 90 degrees. The figure shows another particle P2 of the rigid body P2 is at a distance r2 from the fixed axis, radius r2. The particle P2 moves in a circle radius r2 with the center C2 on the axis. This circle too lies in a plane, so two dimension, perpendicular to the axis, perpendicular to the axis. Note that the circles described by P1 and P2 may lie in different planes also. So both these planes, however, are perpendicular to the fixed axis. For any particle on the axis like P3, r equals to 0. Any such particle remains stationary while the body rotates. This is expected since the axis of rotation is fixed. Axis of rotation is fixed no matter what. So particles remain stationary while the body rotates. Like we have here an oscillating table fan is rotating blades. The pivot of the fan point O is fixed. The blades of the fan are under rotational motion, whereas the axis of rotation of the fan blades is oscillating. In some examples of rotation, however, axis may not be fixed. A prominent example of this kind of rotation is the top spinning in place. We assume that the top does not slip from place to place and so does not have the transitional motion. We know from experience that the axis of such a spinning top moves around a vertical through its point of contact with the ground. Point of contact. Sweeping out a cone as shown. This movement of the axis on of the top around the vertical is termed as precession. Precession. The movement of top on the ground with the point of contact. So now the point of contact of the top with the ground is fixed, doesn't move, change. The axis of rotation of the top at any instant passes through the point of contact. Another simple example of this kind of rotation is oscillating table fan or a pedestal fan. You may have observed that the axis of rotation of such a fan has an oscillating, that is sidewise movement in a horizontal plane but about the vertical through the point at which the axis is pivoted. While the fan rotates and its axis moves sideways, this point is fixed. Thus, in more general case of rotation, such as the rotation of a top or a pedestal fan, one point and not one line of the rigid body is fixed. In this case, the axis is not fixed, but a point is fixed. though it always passes through the fixed point. In our study, however, we mostly deal with simpler and special cases of rotation in which one line, that is the axis, is fixed. Axis is fixed here, but in fans only point is fixed, not the axis. So motion of a rigid body, which is a combination of translation and rotation motion. Illustrate different motions of the same body. Note P is an arbitrary point of the body. O is the center. Arbitrary is the top. Yeah. Center of mass of the body, which is defined in the next section. Suffice to see here that the trajectories of O are the transitional trajectories T1 R1 and T2 R2 of the body. The positions O and P at three different instances of time are shown, respectively, in both figures. As seen, at any instant, the velocities of any particle like O, of P, and the body are in same pure translation. Notice in this case orientation of OP, that is the angle OP makes with a fixed direction, say the horizontal remains the same. That is alpha 1 equals to alpha 2 equals to alpha 3. So this figure B illustrates a case of combination of translational as well as rotation. In this case, at any instance, the velocities of O and P differ. Also, alpha 1, alpha 2, and alpha 3 may be different. Thus, for rotation, we will be about fixed axis only unless stated otherwise. The rolling motion of a cylinder down at inclined plane is a combination of rotation and about a fixed axis and translation. Hence, we shall in the present chapter consider only rotational motion as a fixed axis only. All the best.
Akin na nag-time out.